So we spent some time talking about the origin of the idea of the atom. But remember I said that until recently, nobody's ever actually seen an atom, let alone seen inside of an atom. But still, we have these ideas in these books, in these science books that say, okay, well, we know what the inside of an atom looks like. An atom is made up of protons, neutrons, and electrons. How do we know all of this? We have never, ever seen inside of an atom. All right? We can see atoms, just barely, with really powerful microscopes these days. But we can't see inside of them. So to know what the inside looks like takes some other evidence. Right? We had to put some other evidence together. And again, a lot of this wasn't intentional at first. Let me show you what I mean by this. Okay. So we know that up until the 19th centuries or the 1800s, people started coming around to this idea of, yes, everything was made out of atoms, but they assumed that atoms then were just these solid little spheres, kind of like, microscopic little marbles. They never thought that the inside of them would have been anything. And then this guy comes along, and his name is William Crookes, and he discovers something called the cathode ray tube. Now I would normally show you this in my classroom, but since a lot of you are not in here, then it would be more difficult for you to see this. So here's a picture of generally what we're talking about. So it's this glass tube. It's filled with just a little bit of a gas of some kind, and it's got two metal electrodes on either end. And he figured out that if you pass electricity through that, you get this glowing beam. Kind of cool, but in itself, maybe nothing, extraordinary. But it is very cool. But what people started to do is they started doing experiments with it. And this is where it got interesting. They started thinking about, well, what could you do with this? How could this either be useful, or what could we just learn from this beam of light that seems to shine through this when you pass electricity through it? So it was some years later that there was a man by the name of J.J. Thomson. And he started doing experiments with cathode ray tubes and magnets. And he started wanting to know, this ray that goes through there, that glowing ray, is it actually made out of something, or is it just light? Because if it's just light, magnets won't do anything to it. But JJ hypothesized that maybe it was more than just light that was moving through there. And so he started holding up magnets to it. Now, magnets, again, wouldn't do anything to light. Light isn't made out of any matter, so it shouldn't interact with magnets. But this beam does. And so J.J. Thomson said, you know what? I think that that ray of light that we're looking at is not light at all. It's actually a beam of particles. Let me show you a little quick video of this happening. Right? And you can see in this video that somebody takes a magnet and they hold it up to that cathode ray tube, that beam, and the beam starts to deflect. And what they don't show you in the video is they don't show you if they had turned the magnet around so that the other pole of the magnet was held up to it, that it would deflect the other way. Right? So you can get that beam to deflect one way or the other when you hold a magnet up to it. Okay? So that's strange. And so JJ says, well, there's only one explanation for that. There has to be a charged particle that was within that tube to begin with. Right? And so, well, wait a minute. Well, what was in that tube to begin with? Well, it was a few atoms of a gas. So that means that atoms must have charged particles in them. And he also went further and said, I think it has to be a negative particle, because when we hold the positive side of the magnet up, it runs toward it. And you can kind of see that in this picture here, right? This deflects toward this end of the magnet. This is the positive end of the magnet. Positives and negatives attract to each other. So he says this beam must be a set of negative particles. And the negative particles must have been in the atoms that were in there. So atoms aren't just solid little spheres with nothing to them. They must have a negative particle to them. And since it seems to show up when we pass electricity through it, he went and said, oh, I think we'll call them electrons, because electricity seems to bring them to light. So this idea of what's inside of an atom, JJ wasn't looking for this. He just noticed that this must be the case when he was sort of experimenting with other things that he was doing. And then Robert Millikan, a number of years later, went on further and developed some experiments to determine that the charge of the electron was not just negative, but it was exactly -1. And the mass of an electron was really, really, really tiny. Right? Really tiny. Like almost 2,000 times smaller than the smallest atom that there is. So electrons are really small. Now, we know that atoms are neutral. Atoms don't have a charge. So if there's a negative part to an atom, there's also got to be a positive part to an atom. So then people started looking for experiments, ways of showing evidence that there must have been other particles out there. If atoms have negative particles, electrons, then they must also have positive parts too. Where's the positive part? All right, so the next experiment, which was in the early 1900s, was done by a guy by the name of Ernest Rutherford. And this was really an ingenious experiment. He says, well, okay, so there must be a positive part to the atom. But where is it? We can't see it, so we're going to have to use other methods of determining that it's there. So he says, all right, so we have this positive part. I think it's somewhere in the center of the atom. The positive part is somewhere in the center of the atom. All right? So he calls the center of the atom the nucleus. But he wants to know, how big is this nucleus? So you know what? We're just going to throw things at the atoms, and we're going to see what bounces off. And you think, well, how would you throw things at an atom? Well, he comes up with a way of doing this. He comes up with what is famously now known as the gold foil experiment. And here's how it works. So you've got a radioactive material inside of this box. So radioactivity means that it's spitting out little particles. So they knew at this point in history that radioactive particles, like alpha particles, are little positive pieces of atoms. So he can shoot these little positive particles out of this box by encasing the radioactive material in a lead box with one hole in it. So lead blocks radioactivity. But if you have a hole in it, then the radioactivity that bounces around in there will eventually come out through this hole. It'll escape through this hole. Now, let me just explain to you really quickly. This picture shows this red beam here. Radioactivity is invisible. You wouldn't be able to see it. But just to make it visible on this little diagram, they made it look like a red beam. But in fact, it would be invisible. So we have these invisible little positive particles, these alpha particles, that are escaping out of this hole, and they're traveling down, and they're going to travel towards a set of atoms. Now, Ernest chooses gold because gold is really dense, so all of the atoms should be really close to each other. So that means that if the nucleus is really big part of the atom, then these alpha particles should come and just bounce right off. But if that nucleus, that little positive part of the atom, is really small, then these particles here may be able to go straight through this gold foil. And to know where they hit, since they're invisible, not these red beams, he lines the whole area around the gold foil with this like photographic film. And when these little alpha particles, this radioactive particle, hits the photographic film, it makes a little dot. And so he can see where they hit. And if they come and they bounce off, he'll see lots of areas where they bounce. And if they don't bounce off of anything and they go straight through, he'll see lots of dots here in the back, right behind the gold foil. And it turns out that when he set this whole thing up and he had it go for a while, he got lots and lots and lots of little marks right behind the gold foil. Which tells him the only explanation to that is that there's got to be a positive part, but it must be really small. So this nucleus of the atom, this center of the atom that's positive, must be really, really tiny also. So if you have these really tiny electrons and you have this really tiny positive nucleus, then what's the rest of the atom made out of? And he said, well, it's got to be nothing. I mean, how in the world would these little alpha particles go straight through this really dense gold if it wasn't for the fact that there's almost nothing to an atom? Now, this blew a lot of people away. They're like, wait a minute. So you're saying that the atoms that make up everything, you and me, and tables and chairs and houses and everything, is mostly empty space? And he said, yeah, that's true, right? Most atoms are mostly empty space. That's the only explanation that you get from this evidence. And so we start to build this picture of what we think the atom looks like. We have this tiny little nucleus in the middle. We have these electrons around the outside. And then we have a lot of emptiness between those. And then finally, the last of the pieces of the puzzle is that James Chadwick, again in the 1900s, then concluded that the nucleus, even though it's really small, is not just made out of positive particles. It also has another particle in it. But since we already have a positive proton, and we already have a negative electron, then this third particle that's there must have no charge at all. Since it's neutral, Chadwick called them neutrons. All right, so let's put all of this together. Okay, if we put all of these pieces of evidence together that we've gathered over the years, we now come up with a pretty good picture of what we think the inside of an atom should look like. Again, we don't have any pictures, we just have evidence that shows that we must be right. So we have this tiny little nucleus in the center of the atom. The tiny little nucleus has these positive protons, has these neutral neutrons, and then somewhere floating around the outside of that nucleus is an electron, and it's whizzing around really, really, really fast. Or there might be more than one electron whizzing around really fast. And so it almost makes like a cloud around the outside of where the electrons are. What's the rest of the atom here made out of? Nothing. It is empty space. It's really hard to think of it that way, but that's the way it must be. So, things that I want you to know. I want you to know that an electron is negative, and it's outside of the nucleus in this cloud, and it's really small. You don't have to memorize the numbers, but you need to know that it's really small. A proton is positive. It's in the nucleus, in the center, and it's much bigger than an electron. It's still really small, but it's much bigger than the electron is. And a neutron is also in the nucleus. It doesn't have a charge. It's neutral. And it's about the same size as a proton. So a proton and a neutron exist in the nucleus. The electrons exist around the outside. And in between them is absolutely nothing.